Hey guys, so today I'm going to be interested in the distance information for my data science project. So I have done a few videos, and if you haven't had a chance to check those out, I encourage you to. You can find them on LinkedIn. I might make a playlist later or something like that. But today, the first step in the project is going to be the dissimilarity matrix using the Euclidean distance. So that's just a straight line distance algorithm or mathematical formula to judge the distance between all these points. In my Python code today, it will be just two dimensions. I think that's easy to see, easy to just make sure it works, and it is then generalizable. Oh, I can't even say that. Generalizable for the for more dimensions. Let me give you a quick look at that. If you haven't seen those videos, let me give you a quick look at the data that I'm going to be using so that it kind of makes sense to you. So this is the COVID-19 data, and I'm going to be using people positive and the people total, and I'll take each one of these rows right here as a point, and I'm interested in what is the distance between these as a point. So first I'll take the difference between the x values, each x value, and I'll do the difference between each y value. I'll square them, add them together, square root, that's the Euclidean distance, and there we go. All right, so let me dive into the code real quick, and so I used a Jupyter notebook to really get the simple part of it down, and then generalize it later. So let's see. Let's go back up here. It might be a little bit messy, but that's okay. I did a random matrix, just 2 by 3. I did play around with sizes to make sure they worked, but this one's easy to see. And of course, I only gave it like a high of, well, this is not inclusive, so 5 is my highest number it'll go up to. So I could kind of do some of the math in my head, or at least know what that does not look like, the squared square root or something like that. It's way higher or lower than it should be. And this matrix, just random matrix here, split up into 2 parts, meant to represent the people total and the positive total. Of course, they're in rows. It doesn't really matter for my purposes here because I'm using this technique called broadcasting. And the broadcasting needs both a collimated version of it and a row. So the column and then the row transposed. And the way that Python works when it subtracts a row version and a column version is it actually makes a matrix. And we'll see that in just a second. Here I have the transposed, and this is just well, it's 3 dimensions. I just put this in for understanding, but it actually just uses the x minus t and y minus yt here. This is just the Euclidean metric, and if I needed to generalize it this way, it wouldn't work because I would have to keep on adding, z minus zt, and I don't know, b minus bt, and that sort of thing, and that's going to get annoying, and then I can't go back and do smaller versions. So I obviously need a more, can I say it this time, generalizable algorithm. But this gives me an idea. So I'm going to print out the collimated versions and the broadcasting subtraction, and we'll see what goes from there. As you can see, here's each row collimated. And what's kind of interesting here is, what I think is nice is that the index for the matrix actually tells you what difference I'm taking. What I mean by that is that this is the first row and first column. So that's the first data set, the first point, or first x value, let's say, if we're calling this x and this y. It's the first x value minus the first x value, and this is the second x value minus the first x value, and the third x value minus the first x value, because this is a first column. So the index is 1, 1, 1, 2, and 1, 3. And we can see that here is 5 minus 5 is 0, 1 minus 5 is negative 4, 2 minus 5 is negative 3. And of course it's symmetric because now as we go down, now we start at 2, so this is 1, but 5 minus 1, so it's 4, and then 1 minus 1, and so on. So the index to, this is basically everything minus the second number, this is everything minus the first number, this is everything minus the third number, and so you can kind of, in the index it tells you which one is which, and then same thing for the difference of the y values. Then I'm going to square root and add them together, or I'm going to square them, add them together, and I get this nice array, and this is what the dissimilarity matrix looks like. It has the zeros along the diagonal, and it is completely symmetric, because this is the distance between the first point and the first point, which is 0. This is the distance between the first and second point. This is the distance between the second and first point. Well, it's the same, right? So you can see. So I need the more generalized version, and there we go. That's it. Comes out with the same. If it didn't, that'd be quite embarrassing, and I'd have to refactor it, which probably happened at first. I don't remember. Probably did not happen. It did not come out to be what it should be at first. So plug that in right here so I can use it with the actual COVID that I've read in. And, whoops, I got some spurious stuff here. That's okay. As we can see, the output right here of the dissimilarity matrix isn't really easy to understand. Let me drag this up here to kind of give you a, I did it a couple trials here, but it's not easy to understand just outputting it straight. Maybe I could dress it up a little bit or whatnot. But the nice thing is if you pay attention. So this is actually the first row. Okay, yeah, it goes down a line which confuses everything, but it is the first row right here. And of course this is the second row. Okay, so what's nice is that you can see that the zeros do go down the columns, and if we notice, if this is 2, 1 and this is 1, 2, well, it seems symmetric, but it's still kind of hard to understand this form, and so I did a couple little things, broke it up into the rows. What I noticed about just grabbing one row, so this is just one row, is that the square of those square roots, that distance, it seems kind of high. This is 5,000, 5.7 times 10 to the third. That's 5,700. These are, I don't know if that's a reasonable distance or not, and so I was kind of concerned about them being in the thousands. Maybe it's a reasonable distance. So what I did is I actually took the first one and grab the max value. What's the max value in the first row? And that tells me that the distance between the first point and some point is 6,582. I need to know what that point is, so I was able to extract the row information. That's the 133rd point. So let me see if I can go back here and whoops, that's not what I wanted to do. Okay, so we're gonna okay, so here we have the first point. Okay, so first point. Well, it might be kind of large. It makes sense that it might be kind of large because you have 1 and 0 here and you have thousands. Already I'm kind of looking at that. I want to go to the 133rd. Now, I did this a few times. I don't know if this is exactly the 133rd because Python indexing starts at 0. This is starting at 2. It's confusing the heck out of me. But I do believe they somehow cancel themselves out. If not, you can see some of the ones around it are fairly high. So it does look like 1 and 0, and this could be 6,000 and change. I think that's pretty reasonable. And when I looked at that row and I'm getting the thousands, it's just taking basically what is the distance between 1, because in that algorithm, there was, it would be 1 minus whatever the other one is, 1 minus 6,187, and then that squared plus 0 minus 300, that squared. That makes sense. Okay, so it's, and maybe, because it's squared and then taking the square root would be basically the number almost. I think so. That seems reasonable, but I wanted to do a couple more checks there. So here we go. Let's go back into this data and or the Python code real quick. And I actually broke it down. Let's see if I can find that. I actually broke it down and I said, okay, what is the distance between the 130th? That's this code right here. What is the distance between it? Just that two-dimensional Euclidean distance between the first and the 133rd point, and then I printed it as whether they equal, both of them, and whether they equal each other, and it was true. So it looks like just doing that and my algorithm here inside the function, it looks like they're returning the same thing. So I am pretty confident that this is good to go. And I will do some more three-dimensional testing and see what happens with some of the four-dimensional stuff and so on, and then come back to the 3 dimensions, and then I'm going to be doing my next step. So the next video will be on getting I think it would be the first simplest. Let's actually see if I can take a look here real quick. Yeah, whoop, I'm doing wrong stuff here. Okay, that looks good. Of course, I'm putting a bunch of spurious stuff in my code, so that's great. My hotkeys are working perfectly fine. Okay, so here we have, let's go. Here, okay. So, again, this is the eventual goal. Here is the algorithm. So let's see what our next step is. So we got the point cloud P, that was what was on the screen. We've now measured the dissimilarity. We can arbitrarily define this. Well, I actually might make a slider for this. Maybe I'll do that in the next video, or I will wait. We'll see. And I might just hard code. What this basically is the threshold. So that gives you, if you looked before, it gives you the radius of this the circle that will inform the simplicial complex. But the next step after that is making these lines the first one-dimensional simplex right there. So let's go back to this algorithm. So like I said, point cloud P, dissimilarity matrix, then the threshold distance. Max dimensions I don't need to worry about. I can always stop. Probably stop at 3, right? So I've got K0, that's just my point cloud, but I need K1, which is the lines. And that means graph over it, over the point cloud, using that dissimilarity matrix. And so that should be my next step, is to do this first dimensional simplex. All right, cool. Well, thank you guys so much for watching, and check out those videos. It might make more sense if you check out the other videos. And I look forward to making some more in the future.